Okay, we'll go ahead and get started. So today we're going to look at two reactions of dienes in particular. So that's what we'll focus on in terms of conjugation. Next lecture, I think we'll get into color. So when we start adding more alkenes to a conjugated system, how do they get color? And that has to do with the number of double bonds, the number of molecular orbitals, and then the transitions between them. So today we're going to focus on addition reactions to conjugated systems. And the first one, as I'll point out, can happen in two different ways. And then later on in today's lecture, it's going to happen in a very specific way. But there's a pattern that you can look for to basically say, okay, it came from this type of reaction. So from organic 1, we saw these electrophiles, which I'm showing here is highlighted AB. And in terms of what those could be, so hydrogen, bromine. So those are diatomic molecules where A is equal to B. We had these other situations where we were using solvents like and so then each carbon of the alkene gets something different, so a chlorine and a methoxy group. In this first reaction, we're going to look at the addition of hydrobromic acid. And just as a review, let me put in the lone pairs of electrons on the bromine. So that's delta minus, the hydrogen's delta plus, so it's an acid. And so it's going to add a proton first to the double bond, and then the Br minus is going to trap the intermediate that's formed. In terms of the pattern, so we have this buta-1,3 diene. So we're going to start with this. It's unadorned in the sense that the carbon atoms only have hydrogens. But the other problems we'll look at, we'll start putting stuff on there and seeing how that affects the mechanism. So when we add HBr to buta-1,3 diene, we can see the two products shown, 3-bromo-but-1-ene, and then E1-bromo-but-2-ene. So this is a mono substituted alkene. It only has on this carbon the one substituent coming off it. This is a di-substituted alkene, so it has two substituents. And the E means apart, so those substituents are apart from one another, or we could say trans. And now if you look at the little table beneath, there's temperature in degrees C. For those of you joining new this semester, all the temperatures that we talk about are in degrees Celsius. So again, that's sort of the easiest thing to normalize. So right now we're at about 25 degrees Celsius is room temperature. You know 0 degrees is when water freezes, 100 degrees is when it boils. So I'm going to say the first line here is cold, the second is warm. And we have two products, a 1,2 addition and a 1,4 addition. In the distribution, changes based on the temperature. So first things first, what do we mean by 1,2? That's the relationship of the HBr to the elements present. So here's 1 and 2. That doesn't necessarily mean the location on the carbon chain. It's just those two things relative to one another. So here we have 1, 2, 3, 4. So what do you notice about the 1,4 product is that that central double bond is it's now between 2 and 3. But when you're looking at the starting material, there's no double bond between 2 and 3. So the conjugation is playing a role in why you're getting the double bond migrating. So at cold temperatures, the 1,2 product is favored. And at warmer temperatures, the 1,4 product is favored. So on the next slide here, I'll draw out the mechanism, and then the subsequent slides or questions will talk more about understanding it. So there's the butadiene. So we have delta plus, delta minus. And I'm going to draw it a little lower. And the reason I want to do that is because, as we talked about in Organic 1, that pi bond is going to be the nucleophile. So nucleophile supplies electrons. Electrophile accepts electrons. The issue was with alkenes, you had to decide which carbon, 1 or 2. Since the molecule is symmetric, it could be 3 or 4. Which carbon is going to get the proton? So let's go through both cases and decide. So the arrow is going to originate from the pi bond and abstract that hydrogen. So we start at the 2 electrons of the pi bond. We draw that double-headed arrow that indicates both electrons are moving. And since we're grabbing that hydrogen, we have to break the HBr bond. This should be, okay, that does not allow me to erase. This should be delta minus, sorry. The bromine's delta minus. So that arrowhead points at the delta minus because it's accepting those electrons. So I'm gonna just write C1 here, that gets the H. So that's going to leave us with a carbocation at position 2, and we have to balance that negative charge out with the Br minus. Now the other choice we could have made was protonating C2. Which leaves the carbocation at position 1. And so do you remember the stability trend for carbocations? So tertiary is more stable than secondary, is more stable than primary. So in the lower structure, this is a secondary carbocation. The upper structure is primary. We see that secondary is going to be more stable. So that's going to be the preferred path. And then what's going to happen at this point, and this will further bifurcate. See this original arrow can go in 2 directions. That's called a bifurcation. So this can go in now from here, so 0 degrees cold, where the bromine just automatically traps that position. And that gets the mono-substituted alkene. If we go on the other pathway, which is warm, what's going to happen first is that we're going to look at the resonance structures of that carbocation. Remember that resonance will involve 3 atoms. So you have to have 3 atoms. There has to be a pi bond, either a plus charge, an unpaired electron called a radical, or a lone pair of electrons, negative. So here we have so that resonance form is showing a mono-substituted alkene. If we look at a resonance form, that plus charge is going to migrate over by pushing the arrow like that. So we've gone from secondary to primary, but now this alkene is di-substituted. Another thing about carbocations is they rearrange. And remember, it can only go so primary can go to secondary, secondary can go to tertiary. What I'm showing you is resonance form, so it's both of those things sort of at once, remember. But what's special about this case is that carbon atom is allylic. So remember, allylic is the carbon that's bonded to a double bond. And so it's fine that it forms, it has this primary carbocation. And so at warmer temperatures, the bromine is actually going to trap at that position. Which is going to lead to the 1,4 product. So mono was 1,2. What am I doing? So di is 1,4. So over the next couple slides, we'll go over that kind of step by step. So recalling how alkenes are classified, which of the following correctly describes the products? So I have these terms kinetic and thermodynamic. Kinetic is rate. Thermodynamic is typically stability. So at colder temperatures, that 1,2 product is formed, so that's the kinetic product. When it's warmer, it's the thermodynamic product. And that relates to alkene stability. Where we learned that a tetrasubstituted alkene is the most stable, a monosubstituted alkene is the least stable. And that was from the heat of hydrogenation experiment. So this is dye substituted. This is more stable. So that's going to be our thermodynamic product. So we can eliminate A, and B will be our correct response. As a review and as maybe a reintroduction to the new people joining us, we learned about NMR, so nuclear magnetic resonance, and these uniqueness sets for this very purpose, that if a reaction produces two products, how do we tell those products apart? So if you look at these, I've highlighted the H in both products. Just keep in mind that that's a CH3 group, that's a CH3 group. So don't sort of count that separate when you're thinking about this problem. So it's asking for each one, how many unique proton sets should there be? Go ahead and we'll draw, I'll just draw in the H's and then we can count them. So here's the other two H's. So that's a methyl group. So those three hydrogens are one set. We move over to the next carbon, there's one hydrogen there. So that's another set. We have the alkene. That's a third set. Now on carbon 4, how many hydrogens are there? This carbon right here. So there's two. So are those the same or are they different? So they're both attached to the same carbon, but their relationship to the CH on the prior carbon is different. So these are cis, and then those are trans. So it's going to make those two different. So if we count, we have 1, 2, 3, 4, 5. So that basically eliminates B, C, and D. Let's go ahead and write in the other H's for the second thermodynamic product. So methyl group, that's one set. H here, that's 2. H here, that's 3. And then these two H's are equivalent. So that's going to get you your 4. So as we proceed through this semester, my intention is, to keep pointing these things out. Again, the final exam in this course is cumulative over semesters 1 and 2. So you need to have, the organic 1 material still in your brain as you, see these questions on the final. Be like, well, we didn't cover it this semester, but it's still over the 2 semesters. By what reactive intermediate does this addition reaction proceed? So we said that was a carbocation. So a carbanion is electron deficient. That's always represented by a plus charge. Carbenes, I think we talked about 1 or 2 reactions in the spring about what a carbene is. A carbene is neutral, but it has a lone pair of electrons. So for example, this reagent, so one carbon with two hydrogens, but with a lone pair, that's called a carbene. Sorry, let me explain this. So A, I said, was carbanion, which is electron deficient. It's electron rich, sorry. I'm getting old, and so it's hard for me to like focus on this stuff with my glasses on. That's gonna be my excuse. Let's back up. I'm gonna cross this out. So carbanion is electron rich. So that would be something like CH3, CH2, and then a lone pair and a negative charge. The carbocation is electron deficient. So those will always have a plus charge. And a radical has an unpaired electron. So that's something like CH3, CH2, and then just a dot. So those are the four types of reactive intermediates for carbon. Carbanions, carbenes, carbocations, and radicals. So notice that the carbene and the radical are both neutral, but the carbanion is negative, the carbocation's plus charged. So we saw that using the curved arrow formalism, the mechanism starts by protonating that C1. That gets the carbocation, which we classified. And again, here's the stability trend. So as a review, what is the curved arrow formalism? So we're showing these curved arrows, and since it's double-headed arrow, that means two electrons are moving. When we're talking about radicals, we use a fish hook. That's one electron moving. So we use this term, typically homolytic cleavage for radicals, and then for the double-headed arrows, it was heterolytic. And as a review of what allylic and benzylic means, so that would be an allylic carbon. And if we had benzene, this would be a benzylic. So those are just sort of directions where to look in a molecule. So we said that by protonating carbon 1, that first intermediate is going to be a secondary carbocation. And so I bring this up because one of the things that carbocations can do is rearrange. Remember, primary to secondary, secondary to tertiary. This one will not rearrange. It will form a resonance form, though, so make sure you're clear on those concepts. So this double-headed horizontal arrow means resonance. And so that has two resonance forms, secondary allylic and primary allylic. And then the temperature dictates which one of those gets trapped. We'll talk quite a bit later on in today's lecture again about resonance. But just to refresh your memory, so those are 3 atoms in each case. So 3 atoms. There's got to be a pi bond. And then you're either looking for a plus, a radical, or a minus. So that's what it's telling you is the sort of charge distribution on those 3 atoms in that system. Where is it more, where is it less? And from that, you can predict where the next step in the mechanism is going to happen. So you have the same reagents in there, that buta-1,3-diene, the HBr, and you're altering the product distribution by simply changing the temperature. So whether you set up an ice water bath or you have no bath at all, you can get one of those 2 different products as the major product. Just as a little bit of an aside, from your 255 lab, if you have 2 products, how would you separate them? Like physically separate them? Yeah. So distillation, if the boiling points are sufficiently, if they're both liquids and the boiling points are 10 or more degrees apart, what if they were both solids? How would you separate a mixture of solids? You remember TLC, thin layer chromatography. So TLC would be a way to see if they're separable, and if they are, you could use chromatography. So one of the things we introduced last semester was, we just wrote out the mechanism, but keep in mind that when I talked about this bifurcation point in these pathways, this is an energy diagram where on the y-axis we have energy, and we'll always use kilojoules per mole. Your book may use kilocalories per mole, but the joule is the SI unit, so we'll just talk in those terms. And another thing to realize is that this is always relative energy. It's really almost near impossible to know the absolute energy of a system. So what I mean by relative is we're just this relative to that. We're not looking at the absolute energy requirement of the system, because that's very hard to determine. And why is that? Because remember, sigma bonds rotate, right? So you have that, plus you have this vibrational energy. You have all these different energies, and it's really hard to know that absolutely. So the reaction is of the form, the starting material, diene, can go to one product plus another product. And the distribution really is dependent upon the temperature. So the x-axis is time progressing. Time 0 as the time goes on till all the starting material has been consumed. So we see the starting material well, that's at some energy. And then as time is going on, you can see that that's the bifurcation point where the paths diverge. Then you get this product C, B or C, and they're ultimately at different energies. With the way you interpret this, C is lower energy and B is higher energy. Just qualitatively looking at those curves. So it says which point corresponds to the kinetic product. So A is starting material. B plus C are products. And so if I were to just write the equation, you can see that because they're separated by that arrow. But on here, this is another way of thinking about the mechanism. You're getting to the top of these curves. So that's a part in the mechanism that's not shown just in the reaction itself. So if we draw a straight line sort of across, you see that you have to start going uphill, right? So uphill to get to the top there or the top there. And so those are points on the reaction coordinate that are not isolated, but they have a name. Do you remember what the name is? The transition state. So that's the highest point on the curve, and so in either the red or the blue curve, that's the highest point. That means it's really high energy. So bonds are being broken and made either synchronously, that means at the same time, or asynchronously at different times. So from those points down to that straight line there, you have that distance. So we'll call that transition state B. And then you have that distance, transition state A. And you can tell that it looks easier to get over hill B than it does to C. And so that's just a rate issue. So kinetics deal with rates. So it's easier to get over hill B than it is to C. So product B would be the kinetic product. And so we have now the thermodynamic product, and that again deals with product stability. So we're going to draw that line again, but now we're going to look at the bottom part, not the hills, but the valleys or the wells. So again, the y-axis deals with energy. So the lower you go, the more stable. So we'll just put some dots in there in the well part of B and C. And then if you look at that distance, you can now see that C is greater than B. So that's indicating that the product C is more stable than product B. And again, as we learn more reactions, you'll see that there's different dimensions. You know, you can just see the reaction written as structures. But when you start looking at the reagents in the solvents and the times and temperatures, you see how they affect these curves. And ultimately, the intuition you want to develop is what are the possible products that can form? And then based on the reaction conditions, which one is going to be major versus minor? And then ultimately, using the uniqueness of carbon and proton, how do you differentiate them? So here's a summary slide of that discussion. So A is your starting material. B and C are your two different isomeric products. You have these curves which correspond to the relative energy differences. From the Starting material well going up, that dagger symbol there, that means transition state. So you have two different transition state energies dealing with the rate. And then when you go down, notice that little dot or degree sign. That deals with the Gibbs free energy, so that's the total energy of the system, which is helping you predict the thermodynamic product. So in any of, your final exam might have just one or two of these. You just want to be fluent in looking at this and saying, okay, the top of this is a transition state. I don't see any other things happening, so that has to be a product. But we can also have some other things happen, which we could expand this a little bit more, but I haven't. So something can go up to a transition state, and then if it doesn't go right to the product, there's this other well, and that was an intermediate. So the reaction we saw does have a carbocation intermediate, so we could actually make this curve a little bit more complicated, talking about the stabilities of those different carbocations. So you have starting material, transition state, intermediate, product. And for the most part, you're just visually looking at sort of height differences. I don't think any of the final exams I've ever seen, you're actually calculating anything or dealing with like numbers of comparing. It's just more visual. So let's generalize this now. And so I'll highlight in red. Those are the 4 atoms we're concerned with. In the prior case, we were just looking at that, but now we've taken the terminal atoms, we've tied them together in a ring. Sort of the same analysis is going to be at play. Protonation of the diene with HBr will generate an intermediate best described as what? So if I number the ring like that, again, you have the choice, do you protonate carbon 1 or do you protonate carbon 2? And so you make your decision on what is the stability of the carbocation that results. So if we protonate C1, that gets the proton, the other carbon becomes the carbocation. Or if we protonate C2, first question, how do you classify each carbocation? The bottom one would be what class? Secondary. And then the top one is? It's secondary as well. So what we're doing here, you look at the carbon and then you account for the carbons attached to it. So it is 1 and then 2. So you don't count, there's a hydrogen there, you're not counting it. So it's secondary. So carbon bearing a plus charge, there's 1, 2, that's secondary. They're both secondary, but this one now is next to the double bond, so it's secondary allylic. And so by that fact, it makes this one more stable. Because this top one, that hydrogen's still there, so I'll just draw it in. This top one is just secondary. It can't be stabilized through resonance because it's one away from being allylic. So secondary allylic, so we're going to proceed through that intermediate in predicting the product. So we've gotten to that point. So that was, this H is that H right there. Now the bromine's going to trap that. It says, how many total alkyl bromides will the starting material produce? So when you look at that structure, what's something we have to consider as a review? So is it just that, or is it that plus other things? So remember the structure of a carbocation just in general is the plus charge resides in a p orbital, which has two lobes, a top and a bottom face. So that bromine can trap from the top or the bottom of the plane. And what that does is generate a stereocenter here. And so remember, what was the sort of rule for stereocenters? Huh? So yeah, a stereocenter must have 4 different substituents. And we were going to use the 2 to the n. So here we have 1 stereocenter, n equals 1. So 2 to the 1, that gets us 2 stereoisomers. And we named them R or S, and we'll produce them in a 1-to-1 ratio. And that was called a racemic mixture. So our answer here is B. So I think based on the time, I'm going to skip these next couple slides that still deal with this same reaction. All I've done is move the double bonds around a little bit. I think it would be beneficial if you went through it and sort of did these yourself. What I want to do is get to the next addition reaction of these dying systems. So you're doing the same thing. You have this pattern. This is the pattern. So 1, 2, 3, 4, that's your dying pattern. You're going to protonate, see which carbon gets it, how it's trapped. Any questions on that type of reagent, that type of electrophilic reagent before we move on? So keep in mind, I'm just showing you one type of electrophile, HBr. You can have, the bromine Br2, or you can have the chlorine in water. Those are other type of reagents. Again, the mechanisms is going to be similar. What gets protonated or what reacts first, and then how is it trapped? So you need to be able to extend that to these other types of reagents. So the next reaction, it has a name. So one of the things that's a little bit different this semester is A lot of these reactions are known by the people that discovered them, and so this is called the Diels-Alder cycloaddition. So here's Diels, here's Alder. So those are people's names. Cycloaddition is more of an organic chemistry term. So cyclo means cyclic, and addition is what we're studying now. So a cycloaddition is going to form a ring. And so essentially what we're doing is forming 6-membered rings. The Diels-Alder reaction, it does not do 1-2. It always does a 1-4 addition. So, and there's patterns to the carbon atoms that we're going to look for to say, okay, that has to come from a Diels-Alder reaction. So they won a Nobel Prize in 1950 for this work. So again, I'll have slides with a lot of these Nobel Prize winners because when someone's recognized or a group of scientists is recognized with a Nobel Prize, whether you believe this or not, it really impacts everyone on planet Earth's life. I mean, this reaction is so well utilized that, I mean, you can open any journal and there will be a Diels-Alder reaction in that journal. What's interesting about it is it's not really what they started off trying to do. They were trying to take this compound, cyclopenta-1,3-diene, so there you see the diene. So there's the diene. It's wrapped up in a ring. They were trying to do some other chemistry with this compound called benzoquinone to make some other product. But what they realized based on their structural analysis, they were not seeing that. Instead, what they were seeing is this cycloaddition product. It's also called 4+2. And the way to think about that, you have 1, 2, 3, 4 atoms, and then 1, 2. So it's just accounting for the atoms involved, 4+2. So if I highlight all of these in red here, those 5, total of 5, you'll see them in this product here. So those are those 5 atoms. So what has happened is carbons 1 and 4 of the diene have bonded to carbons 1 and 2 of this just alkene. And overall, I'll highlight in blue, you formed a 6-membered ring. So the Diels-Alder reaction always forms a 6-membered ring, and you're always going to have an alkene in that ring. So it's a cyclohexene. And what they further noticed is that because there's another alkene in that molecule there, another molecule of that starting material, cyclopentadiene, will add to the other side. So the Diels-Alder cycloaddition is very popular in organic chemistry, one of the most popular reactions. Probably the most popular reaction is based on enolate chemistry, which we'll learn in module 3 or 4, I believe. So what's nice about this reaction, see what I'm highlighting here or there? You're forming a carbon-carbon bond and another carbon-carbon bond. So those are pretty powerful in our building our toolbox to make complex molecules. So the issue at the time with Diels and Alder in the 30s, 40s, and 50s is that they ran a reaction, they got a product, they figured out what it was, but they couldn't figure out the mechanism, like the arrow pushing, the curved arrow formalism involved. And so that wasn't really understood until later on in the 1970s when R.B. Woodward at Harvard, Fukui, and Hoffman sort of banded together. So Woodward and Hoffman worked together. Hoffman is a chemist, but he's also basically a mathematician. And he figured out all the equations and things that were needed to adequately describe the mechanism. Fukui did it as well, but in a different way than Hoffman. But they all three won the Nobel Prize in 1965, or excuse me, 1981, for figuring out how this happens. And so, to make a long story short here, what's important is the molecular orbitals. So we talked about when two p orbitals come together, they make a pi bond, and then they make that anti-bonding orbital as well. But as you extend out into conjugated systems, now you have 4 total molecular orbitals, right? 2 are bonding, 2 are anti-bonding. So Woodward and Hoffman figured out you have to match those things in their polarity. So here is that structure. This was the structure of that first cycloaddition. I've redrawn it a little bit different to show you these dotted lines. So this is the starting material, cyclopentadiene. You can see the 1, 2, 3, 4, and then the 5 up is a bridge. And then you have this alkene, and it's showing you that positions 1, positions 1 and 4 are attracted to the alkene. So here's the alkene. And so we can just highlight those throughout. And so we're forming these carbon-carbon sigma bonds, but then we're also left over with this pi bond. So C carbons 2 and 3 here are a sigma bond, but then in the product they end up as a pi bond. So how does this happen? So the pattern you want to look for is a 6-membered ring where somewhere in there there's a pi bond. Then you can say, okay, thinking backwards, that's what this arrow means. It's just a thought experiment. What would I make this from? Well, I could use the butyl 1,3-diene and then this alkene. The 2-carbon unit is called a dienophile. So it's an alkene that has some other group on it. And so that group is what matters. So we'll talk about that. So the mechanism by which they come together. And so I'm showing those orbitals just as these double bond lines. But what will happen is you can think of one of the alkenes as diene acting as a nucleophile to form this bond. The electrons in the alkene going to form the other carbon-carbon bond, and then that pi bond migrating down. So you have 3 arrows. And this all happens in a synchronous fashion. So we use that word so all at the same time. You're forming your 2 sigma bonds to the 1 and the 4 position, and then your pi bond from the 2 to the 3 in that diene. So here's your 6-membered ring with the alkene. So there are some constraints by which this reaction can happen. There's your 1,3-butadiene. The central bond between 2 and 3 is a sigma bond, and we know that sigma bonds can rotate. So there's the same starting material, but the difference between them, they are conformations. So remember, a conformer was a rotation about a bond. This S stands for sigma. See how it says S trans and S cis? Normally when we talk about cis trans, we're talking about double bonds, but the S means rotation about a sigma bond. So S trans means carbons 1 and 2 are on the opposite side of the sigma bond to 3 and 4. So S cis, so 1, C1 to C2, C3 to C4, they're on the same side of that sigma bond. The deal's all their reaction requires S cis. The S trans will not react. So anytime you see a diene that looks like that, it cannot undergo this reaction. So below here are some cyclic dienes that you'll commonly see. So cyclopenta 1,3-diene, furan, which has the oxygen, thiophene sulfur, and now we have a 6-membered ring that's bridged together by 2 carbon atoms. So all of these, the ring makes that locked into the S cis. So there's no way it can become the S trans. So what about the other partner? That's called the dienophile. So the dienophile is an alkene with an electron withdrawing group. So we have to spend some time reviewing what those are and why this is important. The common feature in all of these is the alkene. So I'll highlight those in green. So those are all alkenes, right? A carbon-carbon double bond. And now what's changing is the substituent. So here you have an aldehyde, carboxylic acid, ester, nitrile. Now this is disubstituted, so 2 esters, 2 nitriles. And so that's a requirement, is the alkene must have an electron withdrawing group. What do we mean by that? So there's your just normal alkene. If I substitute one of those H's for an aldehyde, now we have this compound. We know that oxygen's delta minus, carbon's delta plus, just based on differences in electronegativity. And we have a pi bond between carbon and oxygen, so we can draw resonance form. And so what we're doing is looking at the effect of that substituent, that carbonyl group, on the alkene itself. So there's the alkene, but right next door now is a plus charge. So we can draw another resonance form where the pi bond from the carbon-carbon comes over. And now the plus charge is at the terminal carbon. And the minus charge is still on the oxygen. So by electron deficient, what we mean is that the pi bond electron density really doesn't so much reside between the carbon-carbon of the initial alkene, because you have this plus charge at the terminus. And so in these resonance forms, this is going to be a contributor that affects the reactivity. So let's review some of this stuff. Which of these dienes, remember diene is the component with the two alkenes, will not? So what I'll try to do on the exams, anytime something's negative, like not, I'll try to highlight it in bold and caps so you're on the right path. So which one of these will not undergo a Diels-Alder? What's that? C. So in A, there's your diene, it's locked in, so that's the S cis. Here's your diene in B. You still have a sigma bond that can rotate, so that can get into the S cis conformation. Same thing for D, there's your diene. This has a sigma bond that can rotate. Now for C, there's the diene, but everything's locked in those rings. So there's no way for that sigma bond to rotate. So this is S trans, so no Diels-Alder. And again, if you can imagine where the double bonds are, if you imagine those just as the p orbitals, the reason it has to be that way is when this reaction occurs, the p orbitals on carbons 1 and 4 have to be pretty close to each other. If they're farther away, the alkene, when it comes in, cannot engage with it. So looking at now the dienophile, this is the alkene, and it has to have an electron withdrawing group. So again, the opposite of that is electron donating group. So an electron donating group would put more electrons into the double bond. So which one of these is not appropriate for a Diels-Alder? So one of the things that will definitely help you is like expanding out these functional groups into their Lewis dot, looking at the formal charges, and then making your decision. So this is called a nitro group. And we can see that the N and the O are not in their normal valencies. So nitrogen ends up being plus, oxygen minus. Because you have a plus charge on the nitrogen bonded to the alkene, that's going to be an electron withdrawing group. So that is appropriate for Diels-Alder. In B, we have O-ethyl. So So you have an oxygen with its 2 lone pairs of electrons. Those electrons can now donate into the ring. So that's an electron donating group. So that comes down, and then the pi bond puts the electrons at the terminal carbon. So now that's negative. So that's showing a negative charge on one of the carbons that was part of the alkene. So that's an electron donating group. So the answer is going to be B, but let's talk about C. So C does not have a situation for resonance. You have CF3, which is called trifluoromethyl. There's no plus charge, there's no electrons, but we know that fluorine is the most electronegative. So since it's really electronegative, this is called induction. That means through bond. It's like tug of war. So it's basically fluorine's the most electronegative. So through those sigma bonds, it's pulling the electron density from that alkene system. So that is an electron withdrawing group. And then finally you have CN, which is nitrile or cyano. If we expand out the Lewis dot for that, it looks like that. So you have these pi bonds. We can take electron density out of that carbon. So now that carbon's plus. We can do another resonance form. Which shows the plus charge on the terminal carbon of the alkene, so that's electron withdrawing. And so that's how we make our decision about this question. So again, resonance is going to be pretty important for us, not only for the Diels-Alder, but also when we get to aromatic chemistry and we're talking about substitutions, a different type of mechanism. The resonance forms really help us predict what the product is going to be. And again, keep in mind when we draw different resonance forms, they're not 3 separate things. It's still one structure. It's just informing you of, okay, there's more electron density here than there is there. Or there's electron deficiency here versus there. And through that, you're matching how the carbon atoms will attach to one another. So let's do some practice of that. So we have the 3 situations: carbocation, radical, and carbanion. With the carbocation, we need something to push electron density into, and that's going to be the pi bond of the ring. So we have carbons 1, 2, and 3. So this pi bond pushes up. And so the carbocation, therefore, has to be at position 3. And we have even more resonance forms. Again, 3 carbon atoms. That charge is just going to keep migrating to the 3rd position. So overall, that species shows 4 resonance forms. And you can see where the plus charge is and where it is not. 5 minutes. Now again, we have an unpaired electron, so we're not using the double-headed arrow, we're going to use the fish hook. So carbons 1, 2, and 3. So now splitting 2 and 3 is going to be homolytic. So one electron goes there, the other electron goes on 3. So the radical now moves to position 3 there. So this one's going to have 3 resonance forms. And the last one is a carbon anion, so it has a negative charge. Carbons 1, 2, and 3. The lone pair is going to drive the electrons, so double-headed arrow. Now the negative charge will end up on oxygen. So that one has 2 resonance forms. Again, if I can just point out, in this top case, you see the plus charge at the benzylic position, then you see it here, here, and here. Notice the carbon atoms you don't see it on. That's just as important. Again, when it comes to predicting reactivity, where is something, where is not something, or what's lacking? So again, electron donating groups increase electron density into the double bond. Electron withdrawing groups take it out. So if you had this situation, an OCH3 group, so we kind of already saw that in the prior problem. It was just O-ethyl, now it's O-methyl. Oxygen has the lone pairs that can pump into the alkene. So this will be an electron donating group. The nitro group we saw in a prior problem using the help of the Lewis dot structure was electron withdrawing because it has that plus charge right next door to the alkene. In this case, the pi bond comes up, the plus charge moves down. So I think we got less than a minute. I think what we'll do is we'll stop here. You have your next quiz opening at 2:15. You should be able to answer all those questions. What we're going to consider now is we're taking that just regular diene and we're going to stick these electron donating and withdrawing groups on, and we're going to see where those charges end up, because that's going to help us match it to the alkene. And so that'll be a little bit more clear with some of the structures as we look at them.